Okay, today we are going through the thinking processes behind solving a planning question at A level, right? As mentioned just now, the planning question at A level is at the end of paper 2, page 2, paper 2, and 12 marks are allocated. This means that you can afford to spend for 80 minutes on it. Okay, let's begin. Right, first of all, let's look at the question. This question deals with the attenuation of a gamma ray beam, right, through material, right? It's like looking at sunlight through tinted glass, right? The thicker the tinted glass, the dimmer will be the light passing through. That's called attenuation, right? So one way of investigating the attenuation of a gamma ray beam is to measure the half-value thickness. Right? Half-value thickness is the thickness that reduces the intensity of the gamma ray beam to half its original value. Okay? So design an experiment to measure this half-value thickness. Okay? You may assume that you have access to steel plates of varying thicknesses. Right? Gamma ray is very penetrating, right? So you need something like steel or lead to stop it. Right? It's radiation. Okay? You are given a source emitting both alpha and gamma rays and other standard lab equipment. Okay, draw a label diagram and then the standard requirements A, B, C, D, E. Okay, so for the solution, you should structure it according to A, B, C, D, E, even if it feels a bit unnatural at times. All right. Okay, so when you read the question, you must try to understand all its components. So attenuation, even if you don't know the meaning, the question did tell you, right? Right. The question did mention, right? It's a reduction in intensity, right? So obviously, as a physics student, you must know what is intensity. Energy passing through an area, perpendicular to the energy flow, per unit area, per unit time, right? Power per unit area, basically. Okay? So there's a reduction in intensity, like sunlight passing through sunglasses, right? The thicker the glasses, the dimmer the light passing through. Okay? Alright, X-rays are dimmed by lead, okay, and so on. Okay, and so on. Right, okay. So I think you all understand this, huh? Okay. Right, so we go back to the question, we read it carefully, right? The half-value thickness is of a material is the thickness that reduces the intensity of the gamma ray beam to half original value. Okay, so obviously we are measuring the thickness along the direction of the energy flow. Right, no point measuring distance perpendicular. Okay, so we read this definition given by the question carefully. Right. Then the thinking process. We try, because they set it as an A-level exam, right? So obviously they will try to make use of the knowledge that you already have learned earlier in the past 2 years. Okay? So if you look at this definition, you try to relate it to what you have already studied before. Right? So this definition, does it remind you of anything? Half-life, right? It sounds like half-life, right? But instead, half-life is what? Okay. So, so half-life is what? Time taken for the number of unstable nuclei to drop to half the original number, right? Okay? Whereas this one is the distance, right? Okay? That causes it to drop to half the original intensity, right? So there are difference, there's a change in the terms, okay? But the pattern is the same. Okay, so if you apply what you've learned so far, half-value thickness is the thickness that reduces the intensity to half. In other words, if every time the radiation passes through x half the original thickness, the intensity will drop from the starting value to half. Then if you start from here, I0 upon 2, and you pass through another half-value thickness, it will drop by another half. Okay? Right? So you can see there's a huge similarity between this and radioactivity. Right? Radioactive decay. Right? Okay? Okay, except that in radioactive decay, this is not distance, this is time. In radioactive decay, this is not intensity, this is either the number of unstable nuclei in the sample or the activity, the replicates per second, right? Okay, so you have to relate the question, the concepts tested to what you've already learned. Okay, so in the case of half-life, the horizontal axis is time. In the case of half-value thickness, the horizontal distance variable is thickness. In the case of half-life, the vertical axis is number of nuclei. In the case of half-value thickness, the vertical axis is intensity, the amount of energy passing through per unit time per unit area. Okay? Right. So, why do we do this? Because once we can relate it to what we've learned in the past, then we can try to make use of the mathematics that we learned. Right? In the radioactive decay, what did we learn? We know this, right? This is in your lecture notes. Right? So this is the N0, N0 is the starting number of nuclei, N is the number of nuclei left after time t. Lambda is the decay constant, log 2 over t half, right? And t half is of course the half-life. Okay, so can you find a similar relationship that describes this current question? Can you try to modify this equation to what for this question? What do you think about it? Give you a few seconds. Yeah? Sorry? Log 2 over thickness, yes. Alright. So the student mentioned that instead of lambda is log 2 over half-life, now we have another constant is log 2 over the half-value thickness. So we replace the half-life with the half-value thickness. And of course the constant will be a constant relating to this attenuation thing. Right? What about this equation? Can you modify it so that it suits the current problem? Yeah. Instead of n, we can change it to I, right? Instead of n naught, we can change it to I naught. Instead of t, we change it to distance x, the distance we pass through. And lambda is of course this constant. Okay? Right. Okay? So we modify this equation for radioactivity to this new equation for attenuation. Okay? And instead of lambda, I just give it a simple mu, right? It's just a constant, you can use any symbol. Okay? And instead of log 2 over t half, now we have log 2 over x half, where x half is what we're trying to find. Okay? Right. Okay, so far so good. So we have managed to get this equation, right? So what? So what? Where do we go from here? Right, now that you have gotten this, as far as if you are an experimenter, what are you collecting for this experiment? If you are doing this experiment, what are the variables? Yeah, what are the variables? Intensity of the radiation and the distance, the thickness, right? So the variables are, I think most of you can see is x and I, right? The x and the radiation intensity I. So x and I. So you look at this equation, right? Of course, if you're doing an experiment, you want to plot a graph, right? So you're thinking, what is the graph to plot? And because you've been a diligent student, you study this so you can get this. Once you can get this, you try to get the straight line equation, y equals mx plus c. Right? So how do you change this equation into a straight line y equals to mx plus c equation? One, right? Okay. This is just a justification, right? Just a quick revision. Radioactive decay the rate of decay is proportional to the actual number present, right? So if it's a bigger country, more people will die per day, right? Okay, so the actual decay is the actual number present, right? In the case of this one, the rate of reduction in intensity is proportional to the actual intensity. It's like if the rain is heavier, then if it's passing through a sieve, then more of the raindrops will hit obstacles. Okay, if you're firing a machine gun at a fence, right? If you are firing more bullets per second, then obviously more bullets will hit the fence per second, right? So the actual rate of reduction is proportional to the actual bullets flying. Right? The actual intensity of bullets flying through the air. Okay, so there's a parallel, right? So from here you can get this, from here you can get this, right? And so on. Okay, but this page is not essential, right? You can just do a quick relationship and you can get it already. Okay, so as mentioned, once we have gotten this, we try to manipulate it to get into the y equals to mx plus c form, right? So just take ln, right? So keep it can get a bit confusing, right? So you have to be very firm, very clear, and hold on to the variables. You must be very clear what the variables. The variables are x and I. So in your mind, you have to keep track of this I and x. Everything else will be constant, right? Okay, so I naught is a constant, mu is a constant. Everything else is a variable, right? So you just manipulate and then you group the two variables into the y and the x, and everything else will be constant. So if you manipulate carefully, you will see that negative mu is the gradient and ln I naught is the y-intercept. Okay, so once you have concluded this, then in your answer you can say we will plot a graph of ln or log I against x thickness, right? And we can expect to get a straight line with a gradient of minus mu and y-intercept of I naught. Okay, right? Then we look at the question again. The question does not need us to find the I naught, so the y-intercept is not a concern. Our only interest is to find the gradient. Okay, so as you think through, you have to come to these conclusions, right? Okay, right. Now that we have solved the theoretical framework, we can start to answer the question properly. Okay, so now we look at the A, B, C, D, E. A, identification and control of variables. We have the equation already, and we know that mu is related to the half value thickness from here, right? Mu is ln 2 over x half. X half is what we're trying to find, right? So if we find mu, we can find x half. Okay, so conclusion, firstly, we need to plot a graph of ln I against x to get a straight line. The gradient will be negative mu, y-intercept is not important, right? Okay, this question, if you decide to plot a graph of simply I against x, right? In other words, if you simply attempt to draw this graph, the bottom right hand graph, okay, can you find the half value thickness? Can you find this? You can, right? You can just simply measure the I as time as the at various thicknesses, then you get many data points, and just plot, and you get this curve, right? Then you can simply say compare the intensity without anything blocking the radiation to the half value, and then simply find the thickness. Also can. Okay, but because it's a curve, the accuracy will be so high, right? If you intend to use this method, in other words, direct measurement of I versus x, then you will need to block the alpha radiation. Okay, because if you choose to use this method of direct measurement, not using long graph, then your I naught needs to be accurate. So you need to shine the radioactive source directly at the detector, and the radiation that comes out is both alpha and beta. So if you use this method of direct measurement, you need to use something to block the alpha. Maybe just a piece of paper or thick cardboard. Right? Alpha is not by cardboard, right? Okay, or maybe super thick cardboard, right? So the alpha definitely is blocked. So the I naught is due purely to the gamma rays, right? So this is another way which will not be so accurate because of this curve, okay? And let's say you have 6 data points or 8 data points, your x half will be half the value, right? You have to do the approximate curve, okay? Okay, yeah. So, yeah. Right, so for the purposes of answering this question, we have to answer A, identification of variables. So the variables, the independent variable, what we adjust will be the thickness of the steel plates. The dependent variable, what we measure, is the intensity of the transmitted beam, the beam that passes through the steel, right? Okay, the gradient, the magnitude of the gradient gives us the constant, called the attenuation constant. You don't need to know this for answering this question, it's just a name, right? Okay, so you can just say it's constant, right? And then using this relationship, mu is 1 over x half, you can find x half, right? Okay, we also conclude that there's no need to measure the starting intensity I naught. Okay, if you use this method, right? Okay, so you can see that as we think through the question, we are already coming to these conclusions, which you can then write in your answer, right? Okay, part B, equipment you will use. To measure thickness of steel plates accurately, you need vernier calipers or micrometer screw gauge. To measure intensity of the gamma beam passing through, you need a radiation detector, which is typically Geiger molecule. Okay, so this is a real-life GM tube. This is the tube. So the gamma rays go through inside, right? And then the gamma rays, when they hit the argon atoms inside, will cause ionization. So electrons kick out of the atoms, and there is a needle in the center of the tube, and the side of the tube is also metal, and there's a high voltage between them. So if ions are created, the electrons will be attracted towards the anode. The negative remaining ion will go to the cathode. Sorry, the other way around. The electrons will go to the cathode, the ions will go to the anode, and they will cause an electrical spike. Okay? So the electron, when they hit the anode, they will cause a short spike of current. Okay, that's counted by this counter. Okay, depending on how they work. Okay, the one we have in our lab is a counter. Very quick, right? So if it's like intense radiation, they may be used to measure the rate instead. Okay? Right. Okay, we have to address this fact that the source emits both alpha and gamma, but gamma definitely, alpha radiation, helium nuclei definitely cannot pass through steel, so it's not a concern. Okay, so we now have to think of the apparatus. Okay, so properly shielded with the active source, because gamma radiation is dangerous. You have, because the gamma rays will tend to spread out in all directions. So you have some steel plates with a tiny hole in them to try to turn the beam into a parallel beam, right? Okay, this is called collimation, right? Then you have your steel plates. Okay, then you control the thickness, and then you use the GM tube to measure the count rate, right? Okay, so now that you can visualize the apparatus, you can continue to think about control variables. What are the variables that you keep constant? Right? You can keep the distance between the source and the detector constant. Right? Because the radiation will tend to spread out like a torchlight. Right? So if you hold the torchlight far away, the intensity is not so high. But if you hold the torchlight near to your eye, the intensity is very high. So that the radiation, it will spread out. So if we keep the distance from the source to the detector constant, this becomes a constant. This spreading out becomes constant, is no longer affected, right? But if we, between experiments, we change the distance between the source and the detector, then it becomes affected. Okay, right? So we look at the apparatus and we think what are the things we need to keep constant, right? obviously the time taken the count rate, the time over which you measure the counts must be kept constant. You cannot, for one try, you measure for 1 minute, and then the next try you measure for 5 minutes. Obviously the count rate will be different, right? So you need to keep the counts, the duration constant. Okay? You should try to perform the experiment at a fixed location so that the background count stays constant, right? You don't perform the experiment in an indoor environment, and then you do it somewhere else. The radiation coming in from through the ceilings and the windows will be different. Okay? Okay, then we answer the procedure. Right? It's basically translating the diagram into steps. Okay? So set up the apparatus as shown. Use steel plates to coordinate the beam so it comes out roughly parallel. Okay, this can also be thought of as a safety precaution to stop the radiation from spreading all over the place. Okay. Next, we vary the thickness by varying the number of steel plates. Of course, you measure the thickness. Okay, measure the intensity using the GM tube. Right. This is the part I don't like because you're forced to split C and D, whereas it's more natural to just carry on. Okay, but following this format. Okay, so then the cycle is that you repeat these steps. You change X, measure I, change X, measure I, to obtain several corresponding sets of I and X. Then you, as mentioned, as deduced, you plot the graph of non-I against X. Right? And then you find mu from the magnitude of the gradient of the graph. And then you use this relationship to find X half. Okay? Right, then we go into the details of the measurement. Okay, place the number of steel plates stacked together, measure the thickness using verniculars. Then, this is the part that you have to be a bit careful. Because when you measure the intensity of the radiation from the source, it also includes the background count. So, with your physics training in the past few months, you know that there's such a thing as background count. Okay? That means if you are aware when you're answering this question, you will address this problem, right? Okay? So what you actually measure will be the radiation from the source plus the radiation from background count. So you have to, before you perform any measurements, you must first measure the background count. Okay? So let's say you time for 1 minute, how many counts? Let's say 5 counts. Then subsequently, all your measurements can subtract 5, right? Okay, so for each measurement, the total count is recorded by the GM tube over the same fixed period of time. Then the actual count will be what you record, subtract the background count. Okay, and this calculated count is taken as the measure of the intensity. Okay, you can also use count rate. In other words, you take the count over the time. Also can, right? Okay, finally, precautions. Right? First of all, you must ensure that the half-life of the source is big compared to the duration of the experiment. Right? You cannot choose a radioactive source that decays over even a few hours. Right? Every 2 hours drops by half. Then the experiment can't be accurate. Okay, so the source must have a long half-life. Right? Minimum over days. Right? Over several days. So that over, let's say how long you take to do this experiment, maybe 1 hour. Right? Then within that 1 hour, the initial count rate must drop. Must be a constant. Right? So the half-life must be at least 1 week. Right? So that over the course of 1 hour, it doesn't change much. Okay? So again, this is making use of what you've already learned. Okay? So when you're answering such questions, your thinking must be thorough. You must consider all these things. Right? Okay, and of course, as far as possible, you lengthen the time taken for each measurement. Right? You don't measure if the time taken is too short, let's say 10 seconds, then the count will be very small. And then you can't have accuracy. Right? So you must ensure that, okay, because it's a random process. So Okay, so I hope you understand this part. Then finally, safety. Safety is make sure that the source is properly shielded with lead plates, right? Because gamma radiation can cause tissue damage, right, and cancer. Okay. Right. So roughly the process of answering the planning question. Firstly, you look at the question carefully. You try to connect it to the things that you learned in the past. Okay. Identify independent, dependent. If necessary, you quantify the terms. Right? So in this question, they ask for intensity. Right? But you can't actually measure the intensity. Right? Because it is limited by your equipment. The Geiger molar tube, what does it measure? It measures the count rate. Right? It counts the count. It just measures the counts. Right? You can divide by time to get the count rate, but that's still not the intensity. Right? Because the intensity is the energy per unit area per unit time. It's not the count rate. So this is what we mean by quantify. You must translate the variables involved to something that you measure. Okay? Another example is, remember the last year's A-level, they measured the efficiency of the solar panel. Right? So they said efficiency. So how do you quantify efficiency? Because if you can't translate it into a mathematical thing, then you don't know how to measure. Right? So in that question, how do you quantify efficiency? You have to make use of your thermal physics knowledge. Okay? Right, so in this question, thickness is, of course, there's no need to quantify, it's just the thickness. Right? So some things are pretty obvious, but some things you need to translate into mathematical quantity. Okay? From your earlier, the concepts involved, you try to recall the maths relationships, and then from the maths relationship, you can turn it into the y equals mx plus c graph, and then from that you can know what graph to plot. Right? Typically, you try to get a straight line graph. Okay, then from this, the independent and dependent variables, you know what to measure, right? Okay, then once you have a view of the apparatus, you can identify the things that need to be kept constant, and also external factors that can impact the results. For example, background radiation. Okay, then finally think about accuracy and think about safety. Okay? Right. Okay, so that is the thinking process. So once you have done that, you basically put everything into your write-up. Okay, so the write-up looks something like this. Right. Okay, it's basically copy and paste. Right, so first you draw the diagram, then you put part A. Right, so it's a bit like writing a GP essay. Before you start writing, you write down the points on the rough paper, and then you slot it into the relevant sections. Right, independent variable, dependent variable. What should you keep constant? What you should keep constant? What you should keep constant? Equipment you use, right? Okay, then procedure to be followed. Step 1, step 2. In between, slot in the maths working to show why this is the graph that you need to plot. Then tell the marker what you intend to get from the graph, right? Which in this case is the gradient. And then any calculations needed, you also need to spell out. Okay? Then details of measurement, right? In this experiment, the measurements are quite simple, right? Just use vertical to measure. This one, you have to worry about background count, okay? And finally, precautions, right? Okay, which is exactly what I mentioned just now, okay? Okay, that's the process, and you have to do all that in 18 minutes. So, 4 minutes to think and 40 minutes to write down. Right, so for example, the solar panel question in last year, you have to quickly decide what is efficiency. Right? Yeah, you must decide that the temperature, the rise in temperature, measure the volume, the mass that passes, the water that passes through. Right? Okay. Yeah. Okay. Any questions? Yes. Yes. Yeah. Any questions regarding the process of answering planning question? Okay, so your answer must always try to connect to what you've done already. Right? Okay? Okay, any questions? Yes. In this case, you have to make a guess. If not, then you will be doing the basic experiment. Plot I against X and then get a curve. But I think to be able to answer this question, you more or less have to realize that the curve is the exponential decay curve, more or less. Because what they are telling you is that every half value thickness you drop by another half value thickness drop by another half. So I think, anyway, this is set by a school, it's not set by Cambridge. So, yeah. So to have an idea of how Cambridge sets the question, you have to look at the past year Cambridge question. Okay, any questions? In this question, because it's very hard to change the thickness. Because it's based on, it's like, it's very hard to change the thickness of the seed. So your understanding of the concepts must be quite okay to be able to answer the question. Okay, any other questions? All right, if you have questions, please come down to us. If not, we end the lecture. Hopefully,